One of the biggest mysteries in physics is dark matter. Dark matter doesn't emit or absorb light like normal matter, so we can't see it. That means we don't know what dark matter is, even though it makes up most of the matter in the universe. But we do know some things. It has mass, it's been around since the beginning of the universe, and it doesn't interact all that much. Turns out, you could say all the same things about neutrinos. So, could neutrinos be the solution to the dark matter mystery? Let's talk through it today on Even Bananas. To start off, you might be wondering, if scientists don't know what dark matter is, how do they know it exists? We can calculate how certain things should behave, given what we know about gravity and all the particles in the standard model. When we compare this with our observations, we find there's more than meets the eye. There are three big clues I want to point out. First, there's the speed at which galaxies are rotating. Stars on the outskirts of galaxies, where they should feel the pull of gravity less strongly compared to the dense centre, are moving way faster than expected. Second, there's the overall structure of matter in our universe. We see matter in galaxies and galaxy clusters clumped together along strands, like a giant cosmic web. And we also see a pattern of slightly more galaxies than expected being separated by a certain distance. Their pattern looks almost like the ripples on a pond when you throw in a rock. Finally, there's the way that galaxy clusters interact. We've seen that when two galaxy clusters collide, there's a bunch of extra mass on the outskirts, not just at the centre of the collision like we'd expect. A different kind of matter that doesn't show up in our telescopes could provide the extra mass that would explain all these weird observations. And so, we look for dark matter. Now, let's get to whether neutrinos could be the culprit. I'm joined by my fellow June scientist, Asher Kabath, who also studies dark matter with the Lux-Zeppelin experiment. Hi, Asher.
Hi, Kirsty. It's great to be here.
So, Asher, the people want to know, are neutrinos dark matter?
Mostly no, but also a little yes. It's complicated. Like you said, the neutrinos we know from the standard model have a lot in common with dark matter. Both dark matter and neutrinos are not visible in our telescopes. They both have some mass. They're both all throughout the universe. And they each existed early in the universe's history. But we know that dark matter has to be slow-moving enough or massive enough to cause matter to clump together.
It's like trying to gather as many apples as possible while walking through an orchard. You can gather a lot more if you're really tall and walking slowly versus if you're a child running through the trees.
Standard model neutrinos are incredibly light, so they don't interact much through gravity or with one another. They also move incredibly quickly, close to the speed of light. That means they can't cause these dense pockets of things clumping together, and they certainly can't explain the phenomena we see out in the universe. We can run simulations with neutrinos trying to act the part of dark matter early in the universe's history, but instead of things clumping together into stars and galaxies and clusters, we'd end up with enormous rivers of matter spread out across the universe, which is, of course, not what we see.
So when we talk about dark matter, if we mean something that isn't visible and has some of the unseen mass of the universe, then yeah, technically neutrinos fit in. But they can't explain the big observations we're trying to account for. Neutrinos are some of the dark matter, but not the dark matter.
That's right. There are lots of ideas for what might be the dark matter. Two of the most intriguing are the WIMP and the axion. WIMP stands for weakly interacting massive particle, so something big that interacts through a weak force and gravity. Again, this is going to sound sort of like a neutrino. But to cause the gravitational clumping that we see, we need a WIMP that is way more massive than our standard model neutrino, thousands of times heavier.
One possible WIMP candidate could be a really heavy sterile neutrino, but that's not a favoured model. Our data about the known neutrinos tells us that the sterile neutrinos would have to look and behave in a certain way. You'd have to really work at tweaking the models to get a sterile neutrino with the right mass to be dark matter. Other potential WIMP candidates aren't as restricted and could be a better fit.
That's right. And a dark matter particle doesn't have to be really heavy. This is where axions and axion-like particles come in. These candidates would be both really light and extremely common in the universe. Axions would be a type of particle called a boson, which means they'd have different behavior when they're born in the universe. As a result, even though they're light, they would be slow moving enough to cause clumping. This could make them a great fit for the dark matter effects that we see. Researchers are looking for WIMPs and axions in a bunch of different experiments. Some of the WIMP experiments have scaled up to use several tons of very carefully shielded material to look for faint WIMP interactions. These detectors are really sensitive, and they actually have to account for how many neutrinos they might see.
And that's saying something because we know how rarely neutrinos interact.
Axion experiments are also starting to scale up, but they use really different techniques from WIMP searches. For example, some of them use special cavities or magnets to make an electromagnetic field, then wait for an axion to interact and convert into photons. There are some really ingenious ways of looking for dark matter.
You've probably noticed that most of the ways we infer dark matter exists come from measurements not quite matching what we know about mass and gravity. So, what if we just don't understand how gravity works?
There's this idea that we might know how gravity works at the solar system level, but not at the galactic or galactic cluster scale, and we haven't been able to rule this out entirely. But it also doesn't seem particularly convincing. We have an incredible amount of information about how gravity behaves both at really small and really large scales. It's quite hard at this point to make a modified theory of gravity that explains everything we see. Plus, it's very hard to explain our observations of colliding galaxy clusters with modified gravity, but it's really easy with dark matter.
Makes sense. Thanks, Asher.
Thanks, Kirsty.
It's an exciting time to be researching dark matter. Who knows whether there's one dark matter particle or a whole dark sector out there waiting to be discovered? For now, we know that neutrinos play a small part of the dark matter mystery. We'll keep shedding light on the weird world of neutrinos, so make sure to like, share, and subscribe.
Fun fact: the axion is named after a laundry detergent with the same name. Scientists found something puzzling in the fundamental symmetries of the universe, something called the strong CP problem. Axions were originally proposed as a solution and named because they might clean up the issue. What do you think would be a good name for a dark matter particle? Let us know in the comments.